Okay, we're going to work through this sample exam that I posted at D2L, and this is the um, November 2015 midterm. Now, I'm just going to work through the problems. We have a situation where a hand pushes block A, starts from rest, and it gets it up to speed at 15 meters per second. This part of the track is frictionless. It's only this part with the hash marks that has friction. It gets it up to a speed of 15 meters per second, and then block A collides with this more massive block B that's initially at rest. And then right after the collision, we find that block B is moving to the right with a speed of 8 meters per second. And then block B slides across this rough section and eventually comes to a halt. So the first part of this problem asks us to find the force. If the hand is pushing with a constant force of 900 newtons, how far does it have to push in order to get it up to this speed? Now, folks, every problem on the exam is either energy or momentum, and we've got to decide which it is, because if you solve an energy problem with momentum, you get garbage. If you solve a momentum problem with energy, you get garbage. So I'm going to suggest the following little logic table. First of all, we ask ourselves, is this a collision? If yes, then we know that momentum is conserved for every collision, no matter how messy. But this is for the system of everything that collides or interacts. And initial means right before the collision, and final means right after the collision. If the problem is not a collision, then I ask, is time involved? Are we supposed to use the time or find the time? Is time critical to the problem? Now, we know that we never learn anything about time from energy, so if yes, this must be, again, a momentum problem. But in this type of problem, we have to use the general momentum equation, where the initial momentum is equal to the final momentum, except when it's not, and it's not when there's an impulse. That combination of force times time we call impulse. If it's not a collision, and if time's not involved, then it's an energy problem. And then we start E initial is equal to E final, except when it's not. And it's not when there's work done by an external agent. And you remember that work had this funny definition. It's positive force times the distance if those two are in the same direction. It's minus force times the distance if those are in opposite directions. And it's zero if those are perpendicular to each other. Okay, so that's the general decision tree that you'll go through with each problem. So let's go back to this problem. It's not a collision, not yet. We've just gone from here to here. We haven't hit the big block B yet. And we're not dealing with time here, we're dealing with distance. So this is an energy problem. So I start with energy initial is equal to energy final, except when it's not. Now, initially, that would be the initial here, and this would be the final here. I always ask myself the same three questions. Is anything with mass moving? No, not yet. Is anything up off the floor? No. Are any springs stretched or compressed? No. So I've got no energy here. And then the hand does work. Work, werk, it's all tomato, tomato. Is the hand doing positive werk or negative werk? Well, it's pushing in the same direction that the block is moving. So that's positive werk. And it's going to be the normal by the hand times the distance. And then at the final location, I ask myself the same three questions. Is anything with mass moving? Yes. So I have kinetic energy. Is anything up off the floor? No. Any springs stretched or compressed? No. Okay, so there's my equation. Let's plug in what I know. Well, I know 0, and I know the push by the hand is 900 newtons, and I'm looking for delta x, and that's got to equal 1/2 times the mass of the block times this final speed of 15 meters per second squared. Well, at that point, it's just algebra. I mean, it's just plug and chug algebra. And if we solve that for delta x, we get 1/2 meter. Okay. I'm not going to be dragging us through a lot of the steps of algebra here. I assume that you know how to solve an equation for the unknown. Now we deal with the collision. We let that little block hit the big block, and we want to know the velocity, magnitude, and direction of the little block right after the collision. Okay, now again, a collision always starts with this equation, conservation of momentum. And because that's a vector equation, I'm going to need a coordinate system. We'll call to the right positive x, to the left negative x. So right before the collision, I had a 4 kilogram block moving at 15 meters per second. I had an 8 kilogram block moving not at all, and you see that I just wasted ink there. Then the collision happens. I have the 4 kilogram block moving, but I don't know how. I don't know whether it's moving left, whether it bounced back, or whether it kept going forward. So I'm just going to make that a positive variable. And I know that after the collision, this big block, the 8 kilogram block, is moving, we're told, at a speed of 8 meters per second to the right. So that would be positive momentum. So, what does this give me? Over here, I've got 60 franci, and that's got to equal 4 kilograms times V final plus 64 franci. And that means that I've got, if I subtract 64 franci from both sides, I've got negative 4 franci is equal to 4 kilograms V final, or V final is equal to negative 1 meter per second. And that minus sign means left. So I could either write it as negative 1 meter per second with this coordinate system, or I could say 1 meter per second left. But I don't want to do both. I don't want to say negative 1 meter per second left, because negative left is the right to the right. The total kinetic energy of the two-block system right before the collision, well, I have the little block, 4 kilograms, moving at 15 meters per second, and I got to square that. And I've got the big block moving not at all. And you see that I just wasted ink. And this is just plug and chug, and that's going to give me 450 joules. Now, after the collision, my energy is going to be 1/2 times 4 kilograms times the speed of the little block, which is -1 meter per second. But I'm squaring that, so you see that I really didn't need the minus sign. I really don't need the velocity of the little block. I really just need the speed of the little block, which is the magnitude, because that minus sign is going to go away. I've got the big block moving at 8 meters per second, and I've got to square that. And this is going to give me 2 joules plus 256 joules is equal to a total of 258 joules. Now you'll notice that the initial and final are not the same. And that means that this collision is not elastic. And that's because kinetic energy final does not equal kinetic energy initial. Well, does that mean it's inelastic? Well, hold on. There's 3 possibilities. There's maximally inelastic, or elastic. We've just proven with our calculations that it's not elastic. But that leaves 2 possibilities. It's either inelastic or maximally inelastic. So how do I decide? Well, it can't be maximally inelastic. Why? Because the blocks don't stick together. That's the definition of maximally inelastic, is that they stick together and move together after the collision. And that's the type of collision where you lose the most mechanical energy allowed by law. By what law? By Newton's third law. So in order to get these 3 points, you would have had to eliminate both of the other possibilities and then say, oh, it had to be inelastic. So it can't be, whoops, I did it wrong here. It has to be inelastic. It can't be maximally inelastic. Okay. Now this last part, how many seconds will block B slide? Well, this is not a collision anymore. This is after the collision. The collision's already happened. So this is a problem that deals with time. So I would use the general momentum equation. And the initial momentum is going to be right when it starts scraping on the rough section. That's going to be 8 kilograms times 8 meters per second. And then the friction force is going to do negative. Well, let's talk about that friction force. Okay. If I've got a weight force of 80 newtons and a normal force of 80 newtons, then my friction force is going to be mu sub k times that normal force. That's going to be 0.7 times 80 newtons, or 56 newtons. Okay. Now, because that's pointing to the left and I'm calling to the right positive and to the left negative, my initial momentum is going to be to the right, so it's positive. My friction force is going to be to the left, so that's negative 56 newtons times delta T. And when it screeches to a halt, it will no longer have any momentum. And so if I solve that for delta T, I get 1.14 seconds. Okay, let's go now to this two-dimensional collision problem. We've got this asteroid that is coming towards Earth at the just enormous speed of 3 meters per second, 6 miles an hour. We could probably just wait it out. And most of us would probably be in the old folks' home before this thing ever got to us. But anyway, Superman's got to be Superman. He's got to fix everything. And so he comes flying across at a constant speed of 20 meters per second and smashes into the asteroid. And he breaks that into two fragments, and those two fragments are now going to miss the Earth. In the course of the collision, he comes to a rest, and the two fragments go off in different directions. We're told the velocity of fragment 1, but not the velocity of fragment 2. Now, part A is asking for the x and y components of the system comprised of Superman and the asteroid right before the collision. Well, we know that nothing's moving in the y direction, so the momentum initial in the y direction is 0. Okay? But the momentum initial in the x direction, well, I've already defined the positive x direction to be to the right. And so the asteroid is going to have momentum 1,500 kilograms times its speed, 3 meters per second. And then it's moving to the right, so that'll be positive momentum. We've got Superman of 85 kilograms moving at 20 meters per second. And he's moving to the left, so that would be negative momentum. And that gives me a total of 2,800 franci. Okay? So that's the total momentum before the collision. Now the kinetic energy of this system, kinetic energy doesn't have direction. There's no leftward going energy or rightward going energy. There's just energy. So that's going to be the energy of the asteroid plus the energy of the Superman and you see I could have put a minus sign in there, but why bother? It's just going to go away when I square it. And so what that's going to give me is 6,750 joules for the asteroid and 17,000 for the Superman. Oops, those are wrong units. These would be joules. And that gives me a grand total of 23,750 joules. So that's pretty plug and chug. Now, if I want the x and y components of the fragment 1 momentum after the collision, I first of all look at the momentum vector. Well, that momentum vector is going to have magnitude, we'll call that P1 final. P1 final is going to be the mass which is 500 kilograms, times the velocity, which is 4 meters per second. And that's going to be 2,000 franci. So I'm going to have 2,000 franci going in a direction that's 37 degrees below the horizontal. Now, that means my x momentum is going to be positive, and my y momentum is going to be negative, because the x part is going to the right, that's positive, and the y part is going down, that's negative y. Now, this is a 3, 4, 5 triangle, where this is going to be 5 times 400. So this is going to be 4 times 400, or 1,600 franci, and this is going to be 3 times 400, or 1,200 franci. Now you could also have used, this is going to be 2,000 times the cosine of 37 degrees, and this would be 2,000 times the sine of 37 degrees, whatever works best for you. Now, what about the x and y components of the asteroid's fragment 2 momentum after the collision? Well, it's been my experience that this type of problem is always going to be easiest solved if we make a table where we divide up the x part of the motion from the y part of the motion. Now, I know that asteroid 1 has final momentum of 1,600 in the x direction and negative 1,200 in the y direction. We also know that after the collision, Superman's not moving, so he's got no momentum. And we know that the initial momentum is equal to the final momentum. Well, the initial momentum we solved in part A. For the system comprised of everything, I've got positive 2,800 in the x and 0 in the y. Well, all of these parts have to add up to the total. So in order for this to add up to 0, fragment 2 had better have a plus 1,200 franci. And in order for this to add up to 0, in order for this to add up to 2,800, this x part had better be 1,200 franci, positive. Okay? So if I go back and put in that answer, it looks like that. Now, what if I had asked for the total momentum of fragment 2, magnitude and direction? Well, that's going to be a vector made up of those components. So if I've got 1,200 franci, let's put that up a little bit. If I have 1,200 franci in the x direction, and I also have 1,200 franci in the y direction, well, the final momentum of fragment 2 is going to be that sum vector. And you know just by looking at that that's going to be 45 degrees above the horizontal. And to find that total magnitude, I would use Pythagorean theorem. I would go 1200 Franci squared plus 1200 Franci squared. And that's going to give me 1700 Franci. Now, that momentum is equal to the mass of fragment 2 times the velocity of fragment 2. So that means the velocity of fragment 2 is going to be 1700 Franci at 45 degrees divided by 1,000 kilograms. And that's going to give me a final answer of 1.7 meters per second. Okay, and the direction would be 45 degrees above the horizontal. Okay, hokey doodle. Let's go on to the next problem. Okay, this one has springs in it, a track that's frictionless. This just stinks of an energy problem. First thing we want to do is we want to choose the lowest point in the problem to be our floor, to be our height 0. The Werk done by the frictionless hill on the block as it moves from point A to B is going to be 0. And that's because the normal force by the hill on the block is always perpendicular to the motion. Okay? And that's our definition of 0 Werk. We would like to find the kinetic energy at A and what we know is that when it gets to B, the velocity here is 20 meters per second. So I'm going to go from A to B, and I'm going to use my energy initial plus Werk external is equal to energy final. Well, my initial is going to be A because it was there first. My final is going to be B because it got there later in the day. And there's no Werk done by the frictionless track between A and B. So now I ask myself, what types of energy do I have at A? Well, is anything with mass moving? Well, yeah, it must be because they ask us to find that kinetic energy at A. Is anything up off the floor? Well, yeah. Because this is the floor down here. Are any springs stretched or compressed? Well, not when the block is at A. So that's all I've got. And then at B, I ask the same questions. Is anything with mass moving? Well, yeah. And I even know how fast it's moving. Is anything up off the floor? No. We've defined that lowest point to be the floor. So now I just solve this, and I find that the kinetic energy... Whoop, lost my lights. Got to keep moving here. I find that the kinetic energy at A plus the mass, which is going to be 3 kilograms times 10 newtons for each kilogram, times the height is 8 meters. That's got to equal the kinetic energy at B, which is 1/2 times 3 kilograms times the speed of 20 meters per second. And I've got to square that. Well, again, that's just algebra, and if I solve that for the kinetic energy at A, what I get is 360 joules. Okay. Now, if the spring is initially compressed by half a meter, what is the spring constant of the spring required to cause the block to be moving at that speed of 20 meters per second at the bottom of the gully? Well, I can go from the initial point here before we've launched to the final point. I can choose my final point to be either A or B. Okay, it just doesn't matter. Okay, so so let's choose A. Okay, so I know that there's no vert done by the frictionless track. Initially, at this location, nothing's moving, and so I've got no kinetic energy. I do have something off the floor, so I have the potential energy gravitational initial, and I also have a spring compressed, so I have potential energy in the spring initial. And then at A, I've got kinetic energy at A, and I know how big that is. And then I've also got this gravitational potential energy at A. Well, you know, the potential energy gravitational initial is equal to the potential energy gravitational at A. These guys are at the same height. So MGH is going to be the same for both of them. So I can cancel those out. And what I get is that the potential energy in the spring initially is equal to the kinetic energy at A, which is 360 joules. Well, I can also write the potential energy in the spring as 1/2 times K times the compression squared. And now it's just an algebra problem where I can solve for K, and I get 2,880 newtons per meter. Now the acceleration of the block at B is going to be centripetal acceleration. It's moving in a circle there, and so that acceleration points towards the center of the circle, and it has the value v squared over r. Well, that's going to be 20 meters per second squared divided by the radius of that circle, which is 8 meters. And that's going to give me 50 meters per second squared up. Now, I'm looking in this last part for the magnitude of the normal force by the hill on the block at point B. Anytime I'm looking for a force, I draw a free body diagram. So at B, I've got a weight force of the block. And since it's a 3 kilogram block, that's going to be 30 newtons. I also have this normal force by the track on the block. And I drew it bigger than 30 newtons because I know that my diagram has to scream up, because that's the direction of the acceleration. Well, how loud should it scream is given by F net equals MA. If I call up the positive direction, then the net force is just add up all the forces in the y direction. Well, I've got the normal force by the track on the block. It's up, so it's positive. I've got the 30 Newton weight. It's down, so it's negative. That's equal to the mass, which is 3 kilograms, times the acceleration, which is up, so it's positive, and its magnitude is 50 meters per second squared. So that gives me a normal force by the track on the block. If I bring the 30 over to the right, it becomes positive, and then this becomes 150, and I get 180 newtons. Okay. Good job, gang. Okay, let's get through this here. Shannon forgets to depressurize the exit chamber of her space station before she takes her daily space constitutional. That's just a fancy way of saying spacewalk. And is blown away from the station by the explosive decompression with a speed of 50 meters per second. The space station has 100 times the mass of Shannon and is initially not moving. The final speed of the space station will be, well, this is an explosion, and an explosion is a collision. So we would use P initial is equal to P final. Okay. And initially, nothing's moving, so the initial momentum's 0. Afterwards, we have the mass of Shannon moving at 50 meters per second. And we'll say it's moving in the positive direction. We just made that up. But if it's moving in the positive direction, then the space station has to be moving in the negative direction. And it has a mass of 100 times the mass of Shannon. And it's going to be moving at some speed v final. Okay? And so that means v final, I can cancel the mass of Shannon, is going to be 50 meters per second divided by 100, and that's going to be 1/2 meter per second. Okay, so it's going to be C. Which of the following is true for an explosion? Well, an explosion, again, is a collision. And any collision, no matter how messy, even if C4 explosives are involved, conserves momentum. And so that's going to be B. We have a 5 kilogram block sliding on a frictionless table with 15 meters per second, and it collides with a stationary 20 meters per second. Stationary 20 kilogram block. After the collision, the two blocks stick together. What's the final speed of the blocks? This is a collision, so I start here. I'm going to call to the right the positive x direction. And let's assume that everything's moving to the right. So initially I have 5 kilograms moving at 15 meters per second. And I have the 20 kilograms not moving at all. I just wasted ink. Afterwards, there's a collision. That equal sign means the collision. After the collision, they're moving together, so I've got 25 kilograms moving at some v final. Well, this is going to give me 75 franci is equal to 25 kilograms v final. And that's going to give me a v final of 3 meters per second. Okay. Ken Taylor is a teacher in the physics department. He teaches our course for pre-service elementary school teachers. He jumps off the roof of the, this is what the Barnard building used to be called. It stands for Engineering Physical Science Building, but we just called it the Physics Building. The E is silent. On 2 occasions, on one occasion he lands on grass, which brings him to stop in half a second, and the other occasion he lands on concrete, which brings him to a stop in 1/4 of a second. He's not hurt in either case because he's Ken Taylor. Which of the following statements is true? The impulse delivered by the grass is 2 times greater than the impulse delivered by the concrete. The impulse delivered by the grass is 4 times greater than the impulse delivered by the concrete. The impulse delivered by the concrete is 2 times greater than the impulse delivered by the grass. I'm just going to skip right to the right answer. Ken Taylor is going to be going a certain speed right before he hits whatever he hits. And then he's going to stop. So P final is going to be that. So if I write my equation, P initial plus impulse is equal to P final. This is going to be whatever he starts with, and it ends up as 0. Well, that P initial is going to be the same whether he lands on grass or concrete. So that means the impulse is going to be the same whether he lands on grass or concrete. Now remember, the impulse is the force times the time. Well, the force is not going to be the same in both cases. I mean, if he hits a concrete, the force is going to be twice as big because the time to stop is going to be half as big. So it's going to hurt a lot more to land on concrete. But the impulse is the combination, the force times the time. And that's the same either way. So the answer there is E. E. When a 2 kilogram block is dropped on a spring from 9 meters above its equilibrium position, it is seen to compress by 1 meter to bring the block to a momentary stop. What is the spring constant of the spring? So I got this block, I've got this spring, and it has 0 velocity. Okay? And then we drop it, and the spring gets compressed by 1 meter. And we're told that this distance here is 9 meters. Okay? And then the block is stopped again. Well, this is an energy problem. Energy initial plus Verk is equal to energy final. Well, there's no Verk being done because we ignore air resistance. And so we say, what kind of energy do I have initially? Well, is anything with that mass moving? No. Anything up off the floor? Yes. So I have gravitational energy. Is any spring stretched or compressed? No, not yet. Then we go to the final case. Is anything with mass moving? No, it's stopped to turn around. Is anything up off the floor? Well, that depends. Where are we going to call the floor? It's best to always choose the lowest point in the problem to be your height 0. And then you don't have to worry about negative heights. So then, if I choose that to be my 0, there's no gravitational energy at my final event. So all my energy is spring energy. Okay? Now, the thing that made this problem hard, and the reason most people missed it, was because they got the wrong height. They plugged in 9 meters because it started out 9 meters above the top of the spring. But it didn't end up 9 meters below its starting point. It compressed the spring by 1 meter. So it actually dropped 10 meters. So if I call the lowest point in the problem 0, the initial height I've got a mass of 2 kilograms. G is going to be 10 newtons for each kilogram. And the height is going to be 10 meters. And this is going to be 1/2 times K times 1 meter squared. Well, that's going to be a K value of 400 newtons per meter. And that makes the answer D. Most people on the exam chose C, 360. Okay, we're almost there, folks. Good job. We have 2 vehicles. One has 4 times the mass of the other, but they have the same kinetic energies. Okay, so let's start there. Let's see. The kinetic energy of the small vehicle is equal to the kinetic energy of the big vehicle. And that means that 1/2 times the mass of the small times the speed of the small squared is equal to 1/2 times, the mass of the big is going to be 4 times the mass of the small, right? Times the speed of the big squared. And this is going to give me, if I solve for that, the speed of the small squared is going to be 4 times the speed of the big squared. And that means that the small one is going twice as fast as the big one. Well, now let's look at the momentum. We want to compare the momentum of the big vehicle to the momentum of the small vehicle. The momentum of the big one is going to be 4 times the mass of the small one times the velocity or the speed of the small one divided by 2. Okay? And so that means it's going to be twice the mass of the small one times the speed of the small one, or twice the momentum of the small car. So the more massive vehicle has twice the momentum of the less massive vehicle. So I'm going to go back here and put in a B for 6. I have this problem's kind of disconcerting because we've got a charged sphere moving in a magnetic field. Oh my, that sounds like Physics 207. We haven't talked about magnetic fields. We haven't talked about charged particles. But we do know, we're given in this problem, that it's executing uniform circular motion. The magnetic force is causing that uniform circular motion. So if something is going in a circle, its velocity is always tangent to the circle. In order to keep it going in a circle, I have to have a net force, and that's caused by the magnetic force, towards the center of the circle. And so those are going to be perpendicular to each other, and so it does no Verk. We're asked how much Verk does the magnetic force do on that charged sphere. Because the magnetic force is always perpendicular to the motion, it does no Verk. So I go back to my list and I put an A. Okay. Now, a string exerts a tension force of 65 newtons on a 5 kilogram block as it lowers the block a distance of 4 meters. Now, we want to find the change in kinetic energy as this happens. Well, the tension force is up and the displacement is down. So that's going to be negative Verk. Now I know that the Verk external is what changes the energy. And because there's two types of energy here, we can either change the kinetic energy or we can change the gravitational energy. Well, the Verk here is going to be, by the string, is going to be negative 65 newtons times the 4 meters. Well, that's going to be a negative 260 joules. So that's going to be negative 260 joules. The change in potential energy is going to be mg delta H. Well, that's going to be 5 kilograms times 10 newtons for each kilogram times a change in height of negative 4 meters. Well, that's going to be negative 200 joules. So if I go back to this original equation, my change in gravitational energy is going to be a negative 200 joules. And that gives me a change in kinetic energy of negative 60 joules. Well, that makes sense, because if I draw a free body diagram for this block, I've got a weight force of 50 newtons, and I've got a tension force of 65 newtons up. Well, that gives me a net force up, and hence an acceleration up. But the motion is down, so if the acceleration and the velocity are in opposite directions, this block is slowing down as it moves down. And if it's slowing down, it's losing kinetic energy. That's what the minus sign means. My change is negative. And so I'd have C as my answer. I go back and put C in my answer key. Okay, we've got a pendulum problem. It's released from some height, and it collides with a 2-kilogram block at its lowest point. Then it comes to a complete stop. If the block is seen to be moving at 5 meters per second immediately after the collision, what is H? Well, let's see here. We are going to have to, first of all, as this thing swings down, we have an energy problem. So we have energy initial plus Verk is equal to energy final. Well, up here, all my energy is gravitational. Down here, it's all kinetic. Okay? And so I can cancel my mass. It doesn't matter here. And I got 10 meters per second squared times H initial is equal to 1/2 times, oh dear, I just don't know what the V final is. What I do know is that this thing is moving at 5 meters per second. But I don't know how fast this is moving when it gets to the bottom. Oh, okay. Well, I can use what I know about the momentum conservation to solve for this velocity of the ball right before it hits the block. That's a collision. And so I can conserve momentum. Let's call to the right the positive x direction. Right before the collision, I have the ball of mass 1 kilogram moving at some v. We're going to call that v final because it's at the end of the swing. And the block's not moving at all. After the collision, the block's moving at 5 meters per second, and the ball has stopped. So that means that the final velocity of that ball right before it hits the block is going to be 10 meters per second. So now I can bring that up here, 10 meters per second, and suddenly I find that the height is going to be, oh, does anyone see a mistake that I have made? I do. This is squared. Now let me just point out that I've been teaching a long time, 28 years here at this university and years before that. And so what I see over and over again is that the most common mistake that people make on the exam is the one that I just made there. I didn't remember my square. Oh, you'll write it, but you won't do it in your calculator. And that makes all the difference, especially on a multiple choice test. So the answer here is 5 meters, or C. And we'll go back and put C in there. For the same system, the block enters a frictional region shortly after the collision. And how long in seconds will it take to come to a halt? Well, that involves time, so we have to use the general impulse momentum equation. We had 2 kilograms moving at 5 meters per second to the right, so that's positive. We had a friction force acting to the left, and so that's negative times time, and then it comes to a halt. Well, if I knew the friction force, I'd be done. Well, let's draw a free body diagram. I have a weight force of 20 newtons. I have a normal force of 20 newtons. I have a friction force that's equal to mu sub k times the normal force. Well, mu sub k is given as 0.125. So this is the friction force is going to be 0.125. Better put that up a ways. Times the normal force, and that's going to be equal to 2.5 newtons. So what I get is 10 franci minus 2.5 newtons times delta t is equal to 0, and that gives me a delta t of 4 seconds. So I go back and put E as the final answer. Okay, there you go. And that has been that sample exam. I will post that to YouTube.